Welcome, my friends! You are most likely familiar with the idea of exponents. For example, you probably know that 2 times 2 times 2 can be represented by 2 to the third power. Additionally, you might know that something like 2 to the third power times 2 to the second power is just 2 times 2 times 2 times 2 times 2 written out. The first three 2's in red represent 2 to the third power, and the last two 2's in blue represent 2 to the second power. Together, they make 2 to the fifth power. A shortcut is just to add the exponents. 2 to the third power times 2 to the second power is equal to 2 to the 3 plus 2 power, or 2 to the fifth power. This also works for variables. So something like x to the fourth power times x to the fifth power is equal to x to the 4 plus 5 power, which is x to the ninth power. This is what we call the product rule for exponents. If two terms with the same base are multiplied, their powers can be added. Consider the expression negative 3x to the fifth power times negative 4x squared, which we would like to simplify. The key to simplifying an expression like this is to break it up into pieces. We have two different components to our problem, constants and variables. We have the constants negative 3 and negative 4, and we have the variables x to the fifth power and x squared. I like to consider the constants and variables separately, and then put them together at the end. If we multiply the constants of negative 3 and negative 4 together, we get positive 12. If we multiply the variables together, we get x to the seventh power using the product rule by adding the exponents. Putting everything together, our answer is 12x to the seventh power. Sometimes you might have even more pieces multiplied together. Consider the expression 3x times 6x squared y to the sixth times 2y to the fourth. Everything is multiplied together, so we consider this one big term. Just like last time, let's break this into pieces. Our constants are 3, 6, and 2. So multiplying 3 times 6 times 2, we have 3 times 6, which is 18, times 2 is 36. For our x variable, we have x to the first power and x squared. Remember that a variable written by itself is really to the first power, so multiplying we have x to the third power, as we must add the exponents. We have y in two different places, first to the sixth power and then once to the fourth power. Multiplying here, we have y to the 10th power. Putting everything together, our answer is 36 x to the third power, y to the 10th power. Now, I've shown you the table here for convenience, but as you get more comfortable, you most likely won't need to use the table to simplify expressions like this. Okay, consider x squared to the third power. What this literally means is we have x squared 3 times all multiplied together. So one way to write this expression is x squared times x squared times x squared. Well, we know by the product rule that we can add the exponents, so this simplifies to x to the sixth power. In general, we notice a shortcut. If we have an exponent raised to a power, we can then multiply the exponent and the power together to simplify the expression. X squared to the third power is just x to the 2 times 3 power, which is x to the sixth power. This is what we call the power rule for exponents. If an exponent is raised to a power, the exponent and the power can be multiplied. This can also be applied when we have even more complicated expressions. Consider negative 5x to the third power, y squared, all to the third power. To simplify this expression, the power of 3 must be applied to each component. So this expression could be written as negative 5 to the third power times x to the third power to the third power times y squared to the third power. Let's think about negative 5 to the third power first. We know that positive 5 to the third power is 125, but you might remember that any negative number in parentheses raised to an odd power, like the third, fifth, seventh, or ninth power, will still be a negative number. Therefore, our answer is negative 125. X to the third power is just x to the 3 times 3 power, which is x to the ninth power. Y squared to the third power is just y to the 2 times 3 power, which is y to the sixth power. Putting all these three terms together, we have negative 125 x to the 9th power y to the 6th power. We can consider more complicated expressions, like negative x to the 3rd power, y to the 4th power, z to the 3rd power, all squared, times negative 3x to the 2nd power, z to the 3rd power, all cubed. Now, we have two expressions multiplied, but you might remember from order of operations, we need to deal with the exponents first before combining the two multiplied expressions. Let's rewrite the problem with the exponent applied to each component. We have a negative sign out front of the first part, which we'll treat as a constant of negative 1. So we have negative 1 squared times x to the 3rd power squared times y to the 4th power squared times z to the 3rd power squared times negative 3 to the 3rd power times x squared to the 3rd power times z to the 3rd power to the 3rd power. You don't necessarily have to write out the problem in this way, but I think it helps us to understand what's going on, especially when you're first learning. Okay, negative 1 squared in parentheses is positive 1. X to the 3rd power to the 2nd power is x to the 6th power. Y to the 4th power squared is y to the 8th power. Z to the 3rd power squared is z to the 6th power. For the second expression, we have negative 3 to the 3rd power, which is negative 27. X to the 2nd power to the 3rd power is x to the 6th power. Z to the 3rd power to the 3rd power is z to the 9th power. Now we can compare these expressions component by component to do our final simplification. For the constants, we have 1 times negative 27, which is just negative 27. For the x's, we have x to the 6th power times x to the 6th power, which is x to the 12th power. Y to the 8th power stays the same, as it's our only y term. Z to the 6th power times z to the 9th power is z to the 15th power. Altogether, we have negative 27, x to the 12th power, y to the 8th power, z to the 15th power, which is our final simplified expression. Now, you might already know this already, but in case it's been a while for you, remember that any number other than 0 raised to the 0th power is equal to 1. For example, negative 2 to the 0th power in parentheses is equal to 1. Or negative, and then parentheses 2/3 to the 0th power is equal to negative 1, as we apply the exponent first and then the negative sign. Sometimes this will come up in problems with exponents, so make sure to rewrite any powers of 0 as 1. 0 to the 0th power is another undefined expression in mathematics, just like any value divided by 0. It's just something that we can't do. Now, everything we've looked at so far has had a positive exponent. Let's consider some problems with negative exponents. Consider x to the negative 2nd power. Another way to write a negative exponent is to write 1 divided by the exact same expression, but with a positive exponent. So x to the negative 2nd power is the same thing as 1 over x squared. The reverse is also true. So if you have 1 over x to the negative 2nd power, the x term can be brought back up to the numerator with a positive power, as x squared. It's generally desirable to write your final answer without negative exponents if you're asked to simplify an expression. This, of course, applies to constants as well. So, for example, 3 to the negative 2nd power is the same thing as 1 over 3 squared, which is just 1 over 9. Or better yet, something like negative 2 to the negative 3rd power is just 1 over negative 2 to the 3rd power, which is the same thing as 1 over negative 8, or just negative 1 over 8. The answer is negative, as a negative number raised to an odd power will always be a negative number, as we stated earlier. We can simplify expressions using the power or product rules with negative exponents, just like we have with positive exponents. Consider x to the 5th power to the negative 2nd power. The first step is to apply the power rule, which tells us to multiply the exponent of 5 with the power of negative 2. This gives us x to the negative 10th power. Now, like I stated earlier, it's common convention to not write our final answer with negative exponents. So we could rewrite this as 1 over x to the 10th power, which is considered the most simplified form. Something like negative 4y to the negative 4th power can be written as a positive exponent by simply moving the y to the denominator and changing the exponent from negative to positive. Negative 4y to the negative fourth power becomes negative 4 over y to the fourth power. Or something like 1 over 6x to the negative third power can be written with a positive exponent in the numerator as x to the third power over 6. We can have more complicated product rule expressions that involve negative exponents, such as 8u to the sixth power, y to the fourth power, times 2y to the negative fourth power, u, times 6w to the negative ninth power, w to the ninth power. Term by term, we have the constants of 8 times 2 times 6, which is just 8 times 12, or 96. U to the sixth times u is u to the seventh power, since the u by itself has an invisible 1 for the first power, so 6 plus 1 is equal to 7 when we add the exponents. For y, we have y to the fourth times y to the negative fourth, which is just y to the 0 power. For the w terms, we have w to the negative 9 times w to the 9, which is w to the 0. Now, of course, y to the 0 and w to the 0 are both 1, and therefore don't affect our problem, and can be dropped. Putting it all together, we have 96u to the seventh power, which is our final simplified expression. Okay, let's try one final problem. We have 2w to the negative second power, x to the fifth power, all raised to the negative third power. We can apply the exponent of negative 3 to each component individually, which leaves us with 2 to the negative third power times w to the negative second power to the negative third power times x to the fifth power to the negative third power. 2 to the negative third power for our constant is equal to 1 over 2 to the third power, so that piece goes in the denominator. W to the negative second to the negative third power is equal to w to the sixth power, since when we multiply the negative 2 and negative 3 together, we get positive 6. And x to the fifth power to the negative third power is x to the negative 15th power. 2 to the third power is 8, and we can rewrite the x term in the denominator with a positive exponent, since it's generally desirable to have a positive rather than a negative exponent in a simplified expression. The w term doesn't need to change since it's already positive. That leaves us with our final answer of w to the sixth power divided by 8x to the 15th power. Okay, that completes the example portion of this video. I'd like to just quickly summarize all the properties of exponents we have discussed in this video. We discussed the product rule, which states that if two terms with the same base are multiplied, their powers can be added. We discussed the power rule, which states that if an exponent is raised to a power, the exponent and the power can be multiplied. We discussed the zero exponent property, which states that any non-zero value raised to the zero power is equal to 1. We discussed the power of a product rule, which allowed us to distribute the power to each term that was being multiplied together. Finally, we discussed how to deal with negative exponents, being that we could bring them from the numerator to the denominator, or vice versa. There are a few more properties of exponents to discuss, which will be covered in the next video, which will relate to quotients. Alright, my friends, that completes our discussion of the product and power rules for exponents.